towards the automatic, paraphrastic detection of monolingual and cross-lingual plagiarism. So Umaima is here just to give us a few words of her reflections. So, oh wait, first the picture on the thing.
Yeah. Hi, everyone. So thank you so much for, I'm very honored to actually receive the runner-up award for the Kambule Doctor Award. A big thanks to the award committee and to the Indaba organizers. And I would like also, I'm very grateful for everyone who is involved and supported me during my journey. I'm very grateful for my supervisor, my colleagues in my research lab, and family and friends and everyone. Yeah, so thank you so much. Yeah.
Thank you, Meima, for making it with us, and we will continue to look to you as a great representative of what excellent research looks like across our continent, wherever it is, and best of luck in whatever your next steps are. So, and the winner for this year's Kambule Doctoral Award is Dr. Anu Pretorius. Please join me in congratulating him. And Anu's thesis was entitled On Noise Regularized Neural Networks, Initialization, Learning, and Inference. Again, another amazing thesis. I read through it, almost the entire thing. The awards committee came back with shining results, and if any of you are looking for an exemplary thesis which you yourself want to model on, please download it, have a look. We can switch the slides now, and congratulations, but let's do this first.
Good morning, everyone. First of all, it's a deep, deep honor to be the recipient of the Kambule Doctoral Awards. I really want to thank the Indaba and the selection committee for this incredible recognition. And I feel like I grew up with the Indaba through my PhD, and being recognized by the community is incredible honor for me. So I thought instead of going through maybe the technical aspects of my doctoral thesis, it might be more valuable to rather just talk about the lessons that I learned going through my journey getting the PhD. And I really see this as sort of like a personal journey, and I really hope the lessons here, there are only 3 of them, will be valuable for those that are thinking about doing a PhD, or they're busy doing their PhD. And again, I'm saying this is sort of like a personal journey. So, I had a certain context going through my PhD journey, and so I'm not saying this applies to everyone. Everyone's journey is unique, but hopefully you find this valuable. So before I begin saying anything, I really just want to give recognition to my supervisors. So I had 2, Professor Steve Kruin from the Computer Science Division at Stellenbosch University in South Africa, and Professor Herman Kamper, who was from the Department of E&E Engineering at Stellenbosch University. And among the many, many things that they did for me, they particularly gave me very, very detailed feedback on every single line and word that I wrote. And at the time, sometimes when you put in a lot of hours trying to do something, and you submit it to your supervisors, and you get this back, it can be a bit demoralizing or frustrating at times. But really, this is absolute gold. If you have a supervisor that's willing to spend the time to look at your work in this amount of detail, you should be extremely grateful for that. And now that I do research out of university, I sometimes look back at this time and really feel so grateful for the fact that I had supervisors that could dive into the absolute word level detail of what I was writing and give me incredible feedback. So I'm really grateful for them for that. So I started my PhD journey in 2017. And you know, as many do, you kind of have this idea of, okay, I'm going to do this research. It's going to be, you know, some of an uphill battle, but then of course reality is completely different. And I think many people going through the journey will, or who have gone through the journey will share this view that it's quite a, you know, a rough path to walk towards the finish line. And this brings me to the first lesson that I learned, and I'm really, really grateful that I learned it very early in my PhD journey. And it was essentially that your mindset determines what you essentially can achieve. At the time, just before starting the PhD, I was part of a statistics department. I moved to computer science, and the atmosphere in the statistics department was very much like, you know, you'll do a bit of like incremental work, and then maybe you'll submit this to sort of the South African Statistical Association conference, and that was kind of what was expected every year, and there was no real example of you know, venturing beyond that model of publishing research. And so when I started my PhD, this was sort of what I thought I would be doing. I would kind of, you know, try and expand a bit, and I was interested in academia and furthering you know, my research and being maybe part of the university at some stage. But I didn't really have any, you know, grander visions at all. And this all changed because of the first Deep Learning Indaba. So the first Deep Learning Indaba in 2017, that was at Wits University. On the screens are the heroes who started the movement and the community. And maybe we can give them a round of applause. Like, I just think it's... it's no understatement at all to say that the Deep Learning Indaba completely changed my life. I learned so much from the first Indaba, met incredible people, people who I would later do research with, who would become good friends, still very, very good friends to this day. At every Indaba, it's wonderful to see them and see the sort of trajectory that everyone has been going through. And there was one specific moment at the Indaba that really changed everything for me, and it was during the poster sessions. So we were going through posters, and I was really, you know, just blown away by the amazing work. But there was a specific poster by a student called Adam Earle, who was part of Benji Rosman's lab, the Rail lab at Wits. And you know, I didn't know Benji was this director of a Rail lab that was doing high-quality research. I didn't know Adam at the time. They had a visiting academic, Andrew Sachs, who did his PhD at Stanford, and they all were working together on research. And during Adam's sort of, you know, pitch of his poster, I was just blown away about the quality of the work. And at the end, saying that, hey, you know, this poster, this work that I'm presenting was actually published at ICML. And ICML, the International Conference on Machine Learning, was and it is like one of the top venues for machine learning research. And this blew my mind. Like, I was like, here is a local lab, a local student, collaborating with high-profile researchers, publishing at top venues. And it was massively inspirational for me at the time, and it really changed the way I thought about what I would like to achieve during my PhD. So that brings me to the second lesson. There's really no substitute for hard work. I really had this shift in mindset, and I was really motivated, but at the end of the day, you have to put in the hours. You have to really just sit down and do the hard work. And I failed over and over, you know, trying to understand papers, trying to write code, trying to do mathematics. I mean, I think the core paper that I based most of my research on took me months to understand. I probably read it like 100 times. Like, it took me, at some stage I knew it so well, I would go to my supervisor and I would be quoting lines like verbatim on certain sections. And you know, he was quite blown away by this, but that's how many times I read it to try and understand it. So here are some corny quotes on working hard. You see these things and maybe you're like, yeah, okay, whatever. Your future is created by what you do today. Hard work beats talent when talent fails to work hard. And it's easy to sort of, yeah, whatever, I don't care about these things. But there's really grains of truth in all of these. And it goes a long way, really, just like if you want to know what it takes to be successful, it's ultimately like 90% just really, really hard work. And anyone who's reached some sort of success or goal in their life, I think can attest to that. It actually just takes really dedicated hard work. And talent is sort of overrated for sure. The other one I like that I saw was this: work hard in silence and let success make the noise. I think sometimes like people spend a lot of time maintaining social media presences or maybe brand building of themselves, which I think is good and there's a place for that. But I think also to think about the trade-offs of doing that. Like if you rather spend time just reading another textbook or doing problems, exercises, or spending time coding, reinvesting in yourself and your skills, that will then translate in you being better able at achieving your goals, and success will come by itself. You will get recognized by the things you do rather than trying to sort of sell yourself on social media platforms. So after a lot of hard work and really late nights and things, I managed to submit and get a paper accepted at ICML in 2018. And this is a real sort of big achievement for me. And as the Leo meme shows there's a lot that sort of goes into after you've submitted your paper. There's a whole like rebuttal period and discussions, and that really takes a lot out of you, especially if you've done the really hard work of coming with the paper and you're really excited about it and getting your first set of reviews. Especially I think for new PhD students, it's quite tough to receive all the feedback, but then if you really just sit back, take that, and do revisions and things, it can go a long way. There's this really complicated equation, which is something that at the time, or like still today, I'm quite proud of. Like I can't really understand it now, like looking back at it. But what was nice is you would have this thing that looks like this beast of just symbols and things, but would actually describe mathematically how, in this case, there was a study on learning dynamics in linear autoencoder networks. It would describe the evolution of the weights during the network. And what you see in the plot there is actually the theoretical sort of evolution of the weights overlaid with experiments that we did, so empirical experiments, and they match almost exactly, which was, there's almost like this, through the ether of mathematics mapping onto reality in such a way where you have this really complicated expression showing how things work empirically was very, very nice. But then having the paper being accepted, you now have to actually go and present, right? You have to go to the conference. And in 2018, ICML was in Stockholm, which is very far away from South Africa. I didn't have any money. My supervisors didn't have any money. And if you don't go, you don't have the paper accepted, like if you don't present. And so we reached out to the community, specifically to Ulrich, asking for help. So he said, hey, we don't have money, what can we do? And he gave us the advice to go to the Google Travel and Conference Grants, and really gave us a lot of sort of advice of like what to do, how to apply, how to motivate our case. And if there's anyone from Google here, I really want to thank you deeply. Thanks to Google, I was able to go, so I'm deeply grateful. And really, these type of things make an enormous difference, right? Like giving people from Africa the opportunity, and other places in the world the opportunity to go and present their work really, really helps. And I also have at the bottom, it's probably too small, and it's also in Afrikaans. But at the time, talking to Ulrich, he wrote this email, and I underlined the specific sentence here, where he said that if you are not successful in this application, I will actually pay for you to go out of my own pocket. And that was like mind-blowing to me. I was really like, and it just goes to show the sort of caliber of people from the Indaba community and how much they care in terms of supporting people to reach their dreams and present their research. And so, yeah, with the grant, I was able to go, and it was an incredible experience. And this brings me to the last lesson, which is community is everything. I think maybe if you do a PhD, sometimes people do it in quite isolation. So you're working alone, you have semi-regular interactions with your supervisor, and that's about it. But I would really encourage people to not do that. Be part of a community, try and build relationships, form collaborations with people. It absolutely goes a long way to keep you motivated, to inspire you, to have people who can really help you with your research journey. That was definitely the case for me. And so after the ICML paper, there was the Indaba in 2018, which was again an incredible experience. It's the first time I met Karim Bagir, the CEO of InstaDeep, who would later give me the opportunity to start an office in Cape Town for InstaDeep. Him coming to our research at the poster sessions at the Indaba was instrumental in us forming a connection. Standing next to him in the picture is Ilan van Bouillon, who is a great friend and colleague who was in the research lab with me, who I built a great sort of research relationship with, and we ended up publishing at NeurIPS in 2018, and that was at the back there. You can see me discussing the poster with Richard Klein, an academic at the Wits University. And then Riyab, it was also the first time I met her, who's at InstaDeep and would later really become a great friend and person doing research together. And so at the end of 2018, I got the opportunity to go to NeurIPS, and this was the stark contrast between ICML, where it was maybe, I think we were 4 people from, at least I was aware of roughly like 4 people who were there from South Africa at least, and I wasn't aware of anyone from other African countries being there. And then at NeurIPS, it was a completely different story. It was like day and night. There was a huge community. Everyone was wearing their Indaba shirts all the time when they were presenting posters and their work. It was just a first time, I got the opportunity to go to Black in AI, and it was just, again, something that was very, very inspiring and boost your motivation to keep going and keep pressing on. So at the end of 2019, roughly like after the Indaba in Kenya, I had the opportunity to defend my thesis and do it successfully, which was great for me. And I had great examiners. So Andrew Sachs, actually, who was very, very much the person that I built a lot of my work over, Dr. Boubacar Bar, who also played a huge role in my life. Like he invited me to Ames to present my work there. He invited me to a conference in Botswana, which was amazing, to present work there. And then also Professor Etienne Barnard, who gave me great feedback on my research. But I hope through the whole presentation here, and even though this is showing pictures of me celebrating, I hope it's very, very clear that I would not have gotten to this point if it wasn't for a massive community of people who really inspired me, guided me, gave me massive mentorship, and played a huge role in my life, not only incredible recognition and thanks to...
We can take a few questions if there are any, so maybe if you just raise your hand, and then we can just pass the mic around. There will be a mic over there, so any questions? And maybe I'll kick one off if we can, and if you could just give us some insight on what kind of research you are currently looking at, sort of what's exciting you, and sort of where's your journey been since you completed?
Sure. This thesis was very theoretical, like noise regularization, neural networks, trying to understand them mathematically. All the, let's say, experimentation that I did was mainly just to verify that the theory like pans out. And after joining InstaDeep, I literally did like a 180 and started doing reinforcement learning research, which I found very, very interesting. And that's still what.
Well, good morning, everyone. Well, it's actually very nice to see you all from here, finally. So I am presenting the session today. I will start with the usual announcements, but bear with me today. We'll have a bunch of keywords for you to, QR codes for you to actually scan. These are very important, so please pay attention to them. Starting, as always, with the program, updated program. This is particularly important today because we have the workshop starting in various rooms, so please make sure to check which room you are in. I'll stop a minute here for you to scan it. Okay. Moving forward, I don't see any more phones up, okay. Then, talking about workshops, if you are interested in the details of the different workshops, including the speakers and schedules, I invite you to scan this QR code. It will take you to the workshops page, where you have links to each of the websites of the workshops as well. I also stop a minute here. Okay. And last but not least, I really would like to invite you to scan this QR code for feedback on the practicals that happened throughout the week, but also for suggestions for future practicals if you have any. Please be aware that you can actually submit multiple feedbacks, and we invite you to submit one feedback per practicals that you've been to. Thank you very much. Finally, for me, the usual logistical announcements. We really couldn't emphasize enough on the importance of wearing your badges, please. We couldn't allow external people here for your security and the security of everyone. So really, please, it's very important that you wear them. And here you have the Wi-Fi that you can use. Now, before announcing our next speaker, I would like to invite the amazing Eric to tell us about another thing that will make an impact on.
Hi everyone, this is just a very quick announcement. If you love research, if you like AI, and you like scientific discovery, and you want to study more, we have 40 Google DeepMind scholarships for AIMS, African Institute of Mathematical Sciences, in South Africa, for a program that starts on Monday. But the next round of applications will open in a number of months. So please just go to ai.aims.ac.za. I don't have a QR code. The scholarships are only for students who are African nationals and who are based in Africa at the time of application. There are 40 scholarships per year. Please come and join us. It's a one-year program. It's fully funded by the scholarships. We fly to South Africa, teach you, house you, accommodate you. You'll have GPU resources. Yeah, there we go.
Thank you, Eric. Now, it is my great pleasure to introduce our next speaker. So, after learning from the founding fathers of deep learning, with a PhD under the supervision of Joshua Bengio and a postdoc under the supervision of Geoffrey Hinton, Hugo went on to impact both the industry world through startups and joining Twitter and then Google Brain, now Google DeepMind, but also the academic world through his work as an associate professor in Sherbrooke University and then as an adjunct professor of the Université de Montréal and as a chair of CIFAR. He's also involved in multiple conferences, being a board member of ICMon Eichler and chairing multiple versions of them or editions of them. I personally, he works broadly on understanding, developing, and improving deep learning algorithms. And I personally got recently inspired by his work on transfer, meta-learning, and future learning. So it's really with very great pleasure that I welcome Hugo to the Indaba to walk us through perspective on knowledge acquisition and mobilization with neural networks. Welcome, Hugo.
Thanks for the kind introduction. It's really great to be here. I feel really honored to have been invited and privileged. I am talking while I'm connecting, which is tough. Let's see if this works out. I'm now connected on the HDMI. There you go, awesome. So, yeah, thank you for inviting me. Really happy to be here. First time in Accra, loving it already. Looking forward to get the opportunity to chat with many of you, and perhaps some of this presentation can give some grounding of the kinds of things we could talk about. So this is a presentation that essentially covers kind of two things, or goes in two different directions. One of which is going to be technical, so I'll talk about some of the research that I've recently published with my collaborators. So that'll be part of what I do. But also I thought I'd use this as an opportunity to reflect on my own journey, how I got here through the years, and also perhaps sort of use some of that experience to maybe share some of my thoughts, potential advice, and lessons that might be useful for people here who might be early in their journey or starting their journey and making contributions in AI. And then let me try to, I'm going to try to actually have the same display on both my laptop and over here. Let me just try to fix that. All right, displays. Let's see. It's been a while I've done this. How do I mirror display? Okay, well, I can't figure it out, but that's fine. Maybe I'll just then go back to here. Okay, no big deal. All right, you can put my slide back. And on the technical side, essentially what I'll try to feature and advocate for is this view that I like to use when I think about some of the amazing research that is going on right now in AI, which is to think of it as there being two phases, which I call knowledge acquisition and mobilization with neural networks. So I'll talk about that in a little bit, but before I thought I would actually sort of start describing a little bit of my journey and why I am really excited about the current moment that we're in, that I feel is very unique, and in particular in the way that it connects to some of the things that I've had the privilege and the honor to contribute to early on. So I have been doing AI research for over 15 years, which kind of hurts to say. It seems weird to say it out loud. And for a long time, in many ways, I've had the chance to be able to keep working on essentially a single research agenda. And in fact, this slide that you're seeing here, at least for the past 6 years, I've essentially been reusing this slide across my many talks. So trying to focus on always the same question. And essentially the thesis was that with neural networks, with deep learning, we were seeing a lot of success for solving certain tasks where we had a lot of labeled data. And that was really exciting at the time. This takes us back to the quote-unquote ImageNet moment where we started having computer vision systems that were really effective. But obviously that was enabled by the existence of labeled data. And the thought here is, is that going to be sufficient for solving all of the types of tasks that we'd like to solve with AI? There are a lot of tasks where we can't rely on collecting a lot of labeled data. there's in some ways a continuum or almost an infinite number of tasks we might want computers to be able to take on. And so it seems sort of naive to think that for every single task we just collect thousands and thousands of data points labeled, and that's how we'll sort of deploy AI in various areas of our society and technologically. And also, in many ways, this is kind of a really interesting scientific problem. We know as humans we are able to learn new tasks very quickly from very small amounts of personal experience, which would be the equivalent of data for our computers. And so we know in some ways that is possible, to learn things very quickly from a few shots, from small amounts of experience or attempts. And certainly for a long time, this is becoming less and less true, which is why the current moment is exciting. But for a long time, we couldn't really get to satisfactory performance for a task for which we had very little amount of labeled data. So in many ways, from the very beginning of when I started my PhD, this is kind of what we're trying to tackle. So the questions we would explore are things like representation learning in general. In particular, this led me with Pascal Vincent and Pierre-Antoine Mazagol and Yoshua Bengio to explore the notion of denoising autoencoders. And it was actually kind of cool to see Arnaud talk about some of his work that relates to noise in autoencoders and seeing sort of that work sort of continuing in many ways. And at the time, the key idea that we had that we decided to explore was we thought that maybe a way to get a representation that can support many different tasks, enable the ability to generalize to new tasks from small amounts of labeled data would be to do some form of unsupervised learning by training a neural net to discover representation that would be robust to partial corruption of the input patterns. So removing parts of the input and at the output trying to reconstruct the missing bits. And at the time, we were exploring, this idea with very small data sets, notably the MNIST data sets and various variations on it. I'm kind of curious, by show of hand, who knows what the MNIST data set is? I'm trying to, okay, this is not like no one. I've been thinking that, we don't see the MNIST data set all that much anymore, but that's a very, very small, simple data set. It's Jeffrey Hinton's favorite data set, probably. I think he knows every test example by heart. And actually been very useful in exploring some of these ideas. And so that was one of the things that I explored through time. We also had this paper on what at the time we called zero data learning, and which really should have been called zero-shot learning. Zero-shot learning was not something, a concept that really existed at the time, so we were really early thinking about these ideas. Where the idea is that to solve a downstream task that you're faced with, instead of collecting data for it, perhaps there would be a way of actually describing, perhaps in words, what is the task? What are the different, say, classes that you're trying to recognize in natural images, describing those in words as opposed to describing those by providing examples for each. I went back to this paper out of curiosity, just tried to see how we were thinking about the problem, or what was kind of our vision back then. And I sort of took a quote from this where we were saying, it can then be, talk about zero data learning or zero shot learning, can then be considered as falling between human engineered systems, which requires a full manually specified description of a new task solution, and pure machine learning, which requires data for that task to come up with an appropriate model for the solution. And now, I read this, and now we're talking about prompt engineering. So trying to essentially describe with words what is it we're trying to do based on some foundation model or large language model. And so again, like in that context, for me, it's really exciting to kind of see these ideas being pushed so much that they're starting to work really well or allow us to do new things that we couldn't do before. And another piece of work that we explored in the context of this research agenda, trying to be able to generalize to new tasks from small amounts of data, was to look more directly at the problem of few-shot learning, so the problem of solving new tasks from small amounts of data, but trying to tackle this from a meta-learning point of view, that is trying to train systems to learn. So we're designing algorithms that are trying to learn how to learn from examples. And this is something I did with my intern at the time when I was at Twitter and myself. published at iClears a number of years ago now. The idea of meta-learning was certainly not new at the time. There's a tradition, and some people explored this idea much earlier, and that was kind of our way of kind of, taking this idea, give it a bit more air, and sort of revisiting it in the context of the time, in particular the context of few-shot learning. And in many ways now I'm seeing some of these ideas still being present, for instance, in the really nice work in GPT-3 that sort of essentially discovered that when you were doing a form of large language modeling, where you're just taking large amounts of text, predicting the next word from the previous words, you are effectively kind of doing a sort of meta-learning. You are actually discovering an ability to learn from small amounts of examples. That, to me, that's the main actually achievement of that initial paper, is to kind of demonstrate that. And so for me right now, the moment is quite exciting because I'm seeing some connection with some of the early ideas I explored way back many years ago, some very early in my PhD, and some of the things are being achieved right now with the resources that are available, the data that is available. Denoising autoencoders in some ways are sort of found, the same ideas found behind things like BERT or vision mass autoencoders that are quite popular right now for doing some form of foundation model training on large amounts of unlabeled data. Zero-shot learning has really been enabled by GPT-3 and CLIP and other approaches. I talked about how GPT-3 in some ways is also kind of leveraging or discovering that you can do a sort of learning to learn by just training on textual data. And I'm mentioning this because some of these connections, maybe you didn't draw them, maybe you didn't see them between what's happening now and what I did before, and in many ways that's fine, but I think that this is what makes this moment exciting. This is what makes me feel like I belong in this field and why I am a contributor to this field. And I sort of go back to it in terms of a lesson as to the kind of mindset that I would encourage people to have, that is to draw these connections between your work and its contribution within the whole ecosystem, and to actually really lean on that to motivate you in doing research. But before I do that, let's go more in a technical direction, and I'll talk about in particular my view of how we're currently in the current moment we're in AI. Are actually having quite a bit of success in solving a lot of problems that have small amounts of data using deep learning. And to me, the picture that emerges from seeing all of this develop is essentially a process or framework that has two phases. The first one, I'm referring to it as neural knowledge acquisition, where we're essentially training maybe a large language model, a vision backbone with some self-supervised learning, on lots of available data that might come from different sources or that might represent different tasks. But essentially here what we're trying to do is we're trying to kind of capture some knowledge, some information about the written world or the perceived world and put that into the weights of a large neural network. And then there's the next phase, which I refer to as neural knowledge mobilization, where we're trying to take this foundation model, this pre-trained backbone, and we're designing procedures to mobilize this neural knowledge towards your tasks of interest that potentially has small amounts of data, and then allowing this to be done for many different tasks for many different users or practitioners or researchers. And I think right now, there's actually a whole lot of interest on what is going on the left part of this slide, trying to do better neural knowledge acquisition. But I would like to argue and advocate that there also needs to be a lot of research on the right part of this, which is neural knowledge mobilization. And in fact, actually doing research on the right part of this slide here on neural knowledge mobilization is actually much more accessible. It often requires less resources, and we can just leverage all of the work that's being done by the community on the left part. And so that is maybe an opportunity that I would encourage people to think about. There are a lot of open problems in designing better, what I would call neural knowledge mobilization approaches. Right now, in many ways, the state of the art is essentially fine-tuning. The left part would be pre-training, the right part would be fine-tuning. But there's nothing that says that's the only way that we ought to be solving all of these downstream tasks. And we don't even fully understand why fine-tuning works so well. So there's actually a lot of open problems there. There's problems are fairly accessible to tackle. And to sort of, in some way, put my money where my mouth is, I'm going to talk about 3 pieces of work that I've done in the past 3 years that really fully fall in that category of neural knowledge mobilization. So in particular, I'm going to talk about these 3 papers, which have been done either at Mila with some of my collaborators or at previously Google Brain, now Google DeepMind. And before I start, I'll get my bottle of water out. All right, so let's start with the first one. So this is work that I had the chance to do with an intern at Mila and with a faculty who used to be there, Will Hamilton, on the universal representation transformer layer for few-shot image classification. I wasn't sure should I take questions during, should I wait at the end, what's better? At the end, is that the gesture for the end? Yes? Okay. In the end, all right. For this particular paper, and the next one as well, the main sort of problem setting, the picture you should have in your mind is this. We're going to do few-shot image classification. That is, we're going to be in a setting. Oh, okay, I can get my mouse there. That's great. So and this is an example of a one-shot classification problem where we have a very small training set. We have only 1 example per class, and this is a 5-class classification problem. And really what we want is to get from this very small training set the best classifier possible that's going to work well on the test set for this task. Okay, that's going to generalize to new images from these classes. Okay? Now, few-shot can refer to not just 1 example, it could be 5 examples. The idea is that the training set that's here is very small. And that's the challenge we're trying to address. Sometimes the training set in the few-shot learning setting, I'll refer to it as a support set as well. If you hear me say support set, a training set, or a few-shot learning task, it's the same thing. It's just 2 words that are commonly used. And in vision, a lot of people have thought about this problem. How do we enable the ability to learn new visual concepts very quickly, to solve new tasks from small amounts of data? I talked about, the notion of representation learning being kind of an important concept in trying to make progress on these problems. And in particular, some people had advocated for the general concept of a universal representation. So the idea that we would have perhaps some neural net learn a representation, so providing a vectorized feature vector for some images that contains all the features we need to solve any possible or sort of reasonable downstream task. A lot of times, or one approach for doing this that's very simple would be, well, let's say I have a lot of different backbones that have been trained on different sources of data. So in this slide, I might have a data set of handwritten characters, like say MNIST, and maybe I've trained a neural net on that. Maybe I have a data set of instances of bird species, and maybe I have another neural net trained on that, and maybe another one on common objects, maybe like an ImageNet, for instance. One way of getting something towards a universal representation would just be to take all of these neural nets, they're all giving me a feature vector, and I'll just concatenate all of these, and then I'll feed that to some classifier, maybe a linear classifier, and hopefully it can just find the features that are relevant to this downstream task. Now, there's one potential concern with this approach, which is if we really want a universal representation, that means we probably want to concatenate a lot of backbones trained from a lot of different sources, and maybe that vector starts being pretty large. And that could lead, for instance, to problems of overfitting. If you have a very large input vector, even for a linear classifier, the risks of overfitting are real. So in this approach, we thought about the problem slightly differently. So we'll still think about the fact that we'll assume we have some pre-trained backbones. So essentially, we're assuming that this sort of neural knowledge acquisition phase has already been done by someone. Right now, this might sort of mean, I can go on Hugging Face and download different backbones that have been trained in different settings. Instead of thinking of just concatenating all the features, I'll think of the task or the approach for doing few-shot learning as that of just fetching the right backbone for my task amongst all of the backbones that are available to me, all of the pre-trained backbones. Okay, so in the sort of bird's eye view picture of what this means is that for my few-shot learning task, you can think of it as I have a query. So I have something that tells me, here's information about the task that I'm trying to solve right now. And really the query in this case, that would be the task support set or the training set. So this D-train here. Now this query is going to be compared to some keys. And these keys are going to be all of the different pre-trained backbones that are accessible to me that I can potentially fetch to use as my representation for this downstream task. And then the values associated with those keys, that's actually going to be the backbone itself. So the function that if I feed it an image, it's going to give me features that are relevant for this task that I can then sort of use for any other images, in particular the images on the test set, to be able to classify them under my downstream task that's based on a small training set. Okay? And I'm using these terms, query, keys, and values, because I'm going to frame this as sort of a transformer-like architecture. So effectively, it's going to be a single transformer layer that is going to have as a query a representation of the task derived from the training set, is going to sort of compare that query with the keys for each of the pre-trained backbones, and based on whichever key is closest, that's going to tell me which backbone do I use to then map all the images into a feature space and then classify them for that particular task. Okay, that's a high-level picture. And you know, if you just get that, that's probably enough really to understand where we're going. But I'll try to go a little bit more deeply if you're interested, with not with equations so much, but with sort of visualization as to how we more specifically do that with a transformer layer. So we'll go through more details in an example. Let's assume that we have this few-shot learning task. Here it's a two-shot learning task. I have 2 examples of fly agaric and 2 examples of wax cap, which I guess are mushrooms. And then I have a test example I would like to classify. Okay, so it's a two-shot learning problem. It's a binary class, only 2 classes. And under this idea of a universal representation transformer, I want an architecture that's going to tell me from all of these pre-trained backbones that I have, which one should I use to extract features for these images to be able to classify these mushrooms correctly. So in our proposed approach, the first thing that we do is that we will actually apply all of the pre-trained backbones that we have on, well, at first, certainly all of the training images, the images in the support set. So in this visualization, we assume we have 4 pre-trained backbones. These are the 4 different colors that you have here. And so I get a feature vector for each of them. And you can think of this as like the concatenated long vector of all of these. And then based on that, so normally I would want to sort of get attention scores over my pre-trained backbones. I only need 1 set of attention scores if I'm retrieving just 1 backbone. We found in practice that actually doing this first separately for each class and then sort of merging the attention scores works pretty well. So that's what we'll do here. So to get essentially a representation of each class, I'll just take the average of the concatenation of all the pre-trained backbone features under each class. Okay? So this is giving me now 1 vector for the first class, another vector for the second class. I'm calling that f of S1. S1 is all the examples in the training set from class 1, and S2 the examples of class 2. So now I have a vector representation of each class for my problem. And I will leverage that representation to now define a transformer operation where I'm going to compare a query with keys, and that's going to allow me to figure out attention scores on the different backbones to figure out which ones I should be using for this task. So the query is meant to represent the task. And so our approach, we could use another way of representing a task based on the support set. But what we take is just this average vector here, the average vector of all the representations of all the backbones. And that's going to be fed into my attention mechanism. And then the key for the ith backbone is going to be just the average vector of the features of that backbone. Okay, so it's essentially the subvector, one of the subvectors under the query representation. Okay, so this is my other way of kind of having a vector representation of that particular backbone. It's just taking its average features for the task that I'm considering. And so I'm going to have 4 keys. I only have 1 query. And I feed that into this scale.product attention mechanism. So that means I'm going to have essentially a linear transformation applied to both of these vectors. I take the scale.product, pass that through a softmax, and that's going to give me attention scores. So I have 4 backbones. I'm going to have an alpha, an attention score on, I'm going to have 4 of them, 1 for each backbone. All right? And now we decided to do this per class. So we actually have attention scores for each. This is for the situation where maybe one class prefers one backbone, maybe another class prefers another backbone, and then sort of merge that into a single set of attention scores. We just take the average of these attention scores. And now I represent the operation of fetching the right backbone as just taking the linear combination of the vector representations from each backbone. Okay? So now my F bar, which is essentially my operation of getting a representation for my task, is just going to be the weighted average of the feature vectors from each of my backbones Fi, if I want a representation for any image, either from my support set or my test set for my task. So in particular, if I had attention scores that were essentially 1 for just one backbone and 0 for everything else, this would just correspond to taking just the vector from that backbone with an attention of 1. In practice, it's a self-attention mechanism, so we often get some sort of averaging. We actually look at the attention scores and see what kind of structure it learns from experiments. And finally, because we're sort of framing all of this in the language of transformers and of attention mechanisms, so here, effectively, I'm representing the fetching of a single backbone. But maybe my downstream task actually requires multiple representation, not just one. And I can sort of easily extend to fetching more than one backbone by using the notion of attention heads. So I'm going to have more than one attention head, each of which with its own attention parameters. And they're going to learn to coordinate to sort of fetch complementary backbones for solving downstream tasks. So in practice, that's a hyperparameter. We actually find in the experiments we did for the kind of experimental setup we had that fetching 2 backbones was sufficient. So that's the gist of how it's working. If you want more details, you can look up the paper. Again, all of these details don't completely matter to sort of appreciate the next results. All right, so what we'll do here to try to sort of confirm that this approach is actually doing something meaningful, what we'll do is we'll look at the average attention scores for downstream tasks derived from different data sets. So the way we generate few-shot learning tasks when we do these experiments is that we might take, say, I don't know, let's say the Omniglot data set, and then to create, so the Omniglot data set actually has a fair number of examples, but what we'll do is that we will just sample a small subset of its classes, let's say 5 classes. From each of these classes, we'll sample a random subset of images from these class, and then we'll separate these into a support set or a training set and a test set, and that samples a few-shot learning task that we can sort of do an evaluation on. And then we can sort of repeat this process always from Omniglot to get many such, sort of simulate many such few-shot learning classes, and that allows us to sort of have more accuracy around the measurement of the performance of our model. So what you're seeing here is that for each of these columns, you're seeing what is the average attention score that is being learned for few-shot learning tasks that comes from these different sources, these different data sets of few-shot learning tasks. So this is ImageNet, there's Omniglot, aircraft, birds. I guess those are sort of self-explanatory as to what they contain. Quick Draw is actually handwritten drawings of various objects. So they're not numbers typically, they're more like, I think it's like cars or houses or sort of little pictograms. Fungi is mushroom, and VGG flowers, it's a bunch of flowers. And now in this experimental setup, we have pre-trained backbones that were actually also trained on a separate subset of data from these same data sets. So we're going to have a pre-trained backbone from ImageNet, Omniglot, aircraft, and so on. And we also have these 2 sources here that actually, sorry, I said things are the wrong way. So the columns here are the pre-trained backbones, and the rows here are different test sources for the few-shot learning tasks. I flipped things around. And so we have, like, at the bottom 2 rows, these are two other sources of few-shot learning tasks that are not represented explicitly by any pre-trained backbone. So those are really completely new tasks. And what we do here is that we essentially take the average of the weight, the attention weight that's being put for each of these downstream tasks domains on the different pre-trained backbones. So for instance here, let's start with the one on the right. So this is the second head and looking at what kind of attention mechanisms that learns. Where it has learned that if the downstream task comes from ImageNet, well, I should fetch the ImageNet backbone. And when the downstream task comes from Omniglot, I should fetch the Omniglot backbone, and so on. So this makes a lot of sense. It has sort of, even though it wasn't, encoded in this way, from training, it actually discovered to fetch the right backbone naturally. And interestingly, for the two sort of held out domains for which we don't have pre-trained backbones, it did something that as a community we tend to do, which is if it's a new task a new domain I've never seen, I'll just use ImageNet. I'll just use the ImageNet backbone and that'll be most of my representation will come from it. And then we have the second backbone that's going to be retrieved. And what's really interesting is that it tends to sort of find a second backbone that's kind of in an area or domain that's related. So for instance, for Omniglot, so Omniglot is also handwritten characters from different alphabets, whereas QuickDraw is more like symbols than characters. But actually for Omniglot, the second backbone that they decided to retrieve is actually QuickDraw, because it's also handwritten things, okay? So it's kind of like, we can interpret that makes a lot of sense. Let's see. I think there's another one. Oh yeah, a lot of them actually, they're going to complement with ImageNet, which is not all that surprising. And actually for aircrafts, it's use birds, which, kind of makes sense, I guess. Planes are sort of metallic birds, I guess. And so, it sort of discovered something that's kind of meaningful. And in terms of results, at the time, these are somewhat dated. There are better few-shot learning methods now. But at the time, on a benchmark that we had proposed several years before, metadata set, we compared with various methods. And in general, we were often like one of the top performing methods. So on the right, you have sort of the average rank. Sort of confirming that indeed, this idea has legs and works well. Now, this is in some ways somewhat dated. We talk about 2021. There's been a lot of work since then. And I think actually revisiting this idea, though, of thinking of solving downstream tasks efficiently by just retrieving available backbones that other people have trained, I think is kind of interesting. We could probably continue exploring that. We have a Hugging Face that allows for fetching a lot of different pre-trained models. So you could imagine scaling that even more and solving a wider scope of downstream tasks. In fact, I'm pretty sure I've seen some papers recently trying to sort of do that in a sort of more modern way by leveraging large language models as well. And also here, one thing that we did is that we thought of a source for representation as only being the top layer of a pre-trained backbone. And that's it. That's all we would use from a given pre-trained backbone. But maybe there's information elsewhere in that pre-trained backbone that we should also consider fetching. It has a lot of intermediate layers. We sort of forget, but the neural net is kind of a hierarchical model. It has many layers. And each of these layers, they're not always interpretable, but the rough idea behind them is that we think of them as capturing more and more high-level features, but they might be downstream tasks where actually what we want is lower-level features, not high-level features. So another thing that could be considered here is to actually fetch representations, within the backbone, not always just the top one. And that's an idea. The idea of maybe there's information within the backbone that is valuable, but not necessarily at the top. That's another sort of thing that we explored in the next paper that I'll talk about. This was published at ICML last year with my colleague at Google, Utku Evci, Vincent Dumoulin, and Mike Moser, with this method that we refer to as head-to-toe. And it's going to be another flavor of neural knowledge mobilization approach. All right, let's take a little sip. So Here, one of the things that motivated us, that kind of started this project, was that first, the acknowledgement that pre-training and fine-tuning is really effective. In some ways, we don't completely understand why, but it does really work well. It's like oftentimes kind of the baseline to beat, and certainly if you really care about the problem you're trying to solve, you should probably start with that. That's a good first thing to try, if you can. However, it has some drawbacks. Its performance, the accuracy that it delivers is pretty good, it's usually high. But let's say that you have many downstream tasks that you want to solve, well then you have to fine-tune a model for each of these downstream tasks. And that leads to separate copies of your classifier. And if the pre-trained model that you're fine-tuning is actually really, really large, well, that actually might not be practical. Maybe this leads to having way too many large neural nets lying around for all of your different tasks. Instead, maybe you would want something more lightweight, especially if your downstream task has few examples, you might expect the classifier to require few additional parameters, and not completely newly instantiated neural net classifier. And this is effectively the problem we tried to approach. Can we reach the performance of something like fine-tuning, that is just taking a pre-trained backbone, initializing a new neural net with it, adding a softmax layer for my downstream classification problem, and then adjusting all the weights, including the internal one? So can we sort of at least match or even beat this approach, but with something that's much more lightweight, that has, that trains more quickly, and that ends up requiring additional parameters that are a small fraction of the original pre-trained model, as opposed to all of the pre-trained model. Now, there is an approach that has these property of efficiency and not requiring a lot of additional parameters, and that's what's often referred to as the linear probe approach. So what linear probe is just that you take a pre-trained backbone, you use it to extract features from all of your data set, and now you just train a linear classifier on these features without actually changing the backbone that delivered the features. So that is considered fixed. It's a fixed feature extractor. All that you're training is the top classifier, and the top classifier tends to be linear. So it's just essentially just a softmax layer added where you're only updating those weights. So it's pretty efficient. You're just training a linear classifier. You can do that very quickly. It's not a lot of weights that are typically going to be in this output layer. But in general, its performance tends to be lower accuracy than pre-train and fine-tuning. So we see this here in this illustration. What you have at the bottom is a list of a number of image classification problems, and they've been ordered by how similar they are with ImageNet, with a metric that I'll describe in the next slide. But essentially here you have types of natural images with concepts that are actually found in ImageNet. And on the left, you essentially have, a lot of these are essentially synthetic data sets. Some of these are not even pictures, they're really synthetic. We're comparing with ImageNet here in terms of similarity, because that's what we'll use as our pre-trained backbone in our experiments. We use a pre-trained ImageNet model. And in this graph here, you have the dotted line that corresponds to doing linear probe. So just a linear classifier on the features at the top. And the fine-tuning is the solid line here. And what you'll notice first is, well, actually, fine-tuning is pretty much always better than linear probe. It's actually kind of surprising, in fact. So some of these data sets don't have a lot of examples, and you would think that training a large neural net on it, even though it's pre-trained and pre-initialized, would perhaps for small data sets, small training sets, start overfitting. But actually in practice, if you use some decent early stopping approach, you regularize well, we actually don't see that as much. And instead, we seem to find linear probe tends to underfit. The situations where a linear probe kind of matches fine-tuning are the situations where the data set, the downstream data set, is similar to ImageNet, those on the right. And again, that kind of makes sense. It sort of suggests that by training on ImageNet, you probably have a decent representation, so you don't really need to tune it. All you need is just get a new classifier for this new set of classes that you're trying to classify. But on the left, the gap between linear probe and fine-tuning starts being pretty large. So this is where there is a gap. This is where we should try to figure out a way to take something like linear probe, but lift its ability to generalize to very different downstream tasks with data that's quite different from the pre-trained model. And our simple approach to do this, so we're going to try to do something like linear probe, so that's efficient. But we're going to try to think as to why is it that maybe fine-tuning works. And one hypothesis that we laid out is that maybe all that fine-tuning is doing is that by tuning the weights of the neural net, the internal weights, it's taking some information that never makes its way all the way up to the top layer. It's making now that accessible by just tuning the various weights, making sure the ReLUs aren't blocking, aren't saturated at 0 and not passing information. And maybe this is all that it's doing. If that was the case, then one approach to fix that instead is to just say, well, let's just have a linear classifier that has access to many internal layers, not just the top layer. So very simple idea. It does mean that we have now a linear classifier, so you can think of this as, this is now a linear classifier with a concatenation of many features. And I mentioned there's a risk of overfitting if we do this. And the way we'll address that overfitting is that we will actually apply a lot of regularization on this linear classifier. And in fact, we'll make it sparse. And the other benefit of making it sparse, so by a lot of its weights being 0, is that the number of non-zero weights, which is the only thing we'll need to store in the end, will be small. And so we actually have a method that doesn't take a lot of memory, that doesn't take a lot of space to store, and still, we're training a linear classifier, so it's actually fairly efficient. And so that's the idea of head to toe. Head to toe comes from the fact that we're taking layers from head to toe from the backbone. So the comparison is visualized here between linear and head to toe. So we have this top linear classifier, and then it is accessing not just the top features, but also some of the intermediate ones. And some of them it's actually, in the end, not using at all. And it won't be using them thanks to our sparsity regularization. We're going to train a sparse linear classifier here. And so I won't go over the technical details as to how we achieve all of this. You got the gist of what I'm doing, and you can check out the paper for the details. But one of the things that we can do now is compare the performance between head to toe and linear. So just take the difference between their accuracies. And then we'll look at different data sets, and we'll rank them by their similarity with ImageNet. So on the left, we have the most dissimilar. On the right, the most similar. This similarity is essentially, it's kind of interesting, so I'll explain it here. So what we do is that we actually take the accuracy of linear probe on a data set from that, on a task from that source, from that data set, and then we'll compare it with training from scratch. So not pre-training with ImageNet, just using random weights for the same backbone and then training all of it. And so the idea is that if the data set, the downstream data set is similar to ImageNet, well, if training from scratch will discover similar features from the features discovered by ImageNet, which is what the linear probe is using, and therefore the accuracy should be similar. Well, that's a simple idea, and generally when we look at the ranking of the data set, it sort of makes sense. And what we're seeing here, so is the gap between how much better is head-to-toe doing compared to linear for these different data sets. And we do see for those that are quite different from ImageNet, indeed with head-to-toe, we really boost the performance. In particular on these, like, they're called structured data set. They're really like this sort of, some of them are kind of synthetic data sets. And very rarely does it actually do worse by doing head-to-toe. And so we now can look at the full set of results. Here, we took another benchmark, which isn't metadata set as in the previous paper. It's called VTAB, which you might know. It has many more data sets in this kind of characterization in natural, specialized, and structured data set. And what we do find is that head-to-toe, on average across these problems, has a performance that is sort of slightly better, but essentially the same as just pre-trained and fine-tuning. But it takes a small percentage of the additional parameters. It trains much faster. And one of the ways in which it catches up on linear probe, as I said, is that it actually does pretty well in these sort of structured data set, that some of which are synthetic. All right, so in some ways, it kind of gives legitimacy to this idea that maybe fine-tuning is just surfacing features that are in the internal backbone. In some ways, it doesn't completely. Sometimes fine-tuning does do better than head-to-toe, and sometimes it's the opposite. But I think maybe there's more to explore to this potential hypothesis. And just generally speaking, I would argue that research that aims to understand why is fine-tuning so successful by maybe finding other mechanisms that end up being about as performant, I think is a very interesting area of research to explore. All right. And then for the last paper, we'll shift gear completely in terms of what kinds of problems it look like. So instead of looking at image classification, we're going to look at code completion, so using machine learning to produce code. And this is work that was just presented at ICML by my PhD student at Mila, Disha Srivastava, and the co-advisor, my colleague at Google, Danny Tarlow. So Disha, who just completed her thesis and is starting at Google DeepMind. So the problem setting that we'll look at is what we call line completion. The way this works, the way we set up the problem is that, let's say you have a repository of code. What you would like to achieve is to be able to sort of position your pointer somewhere and be able to complete that line. So sort of simulating the fact that maybe you've written all of this code so far, and now you're here and you want to write the rest of this line, and you'd like some software to kind of tell you, where's what I think maybe you want to actually code. And if that works great, that accelerates your workflow. You get to just complete the line and move on. And so the way we can both train large language models on this task and also use them is by feeding as input the preceding context of where you are, where your sort of simulated cursor is in your data set. And then you train your model to just produce the rest of that line. Okay? And really, when you train large language models on data sets of code, that's effectively what you're doing at every single position in that file. You're just going one position after another and producing everything else that's left or to the right of it or bottom of it. Now, in some ways, we know that now that this is actually a very successful area of using large language models. But if you just take that somewhat naive approach to just say, well, from just what's been written in that file preceding to my cursor, I can complete accurately the rest of the line. In some ways, in some situations, you can imagine that's maybe impossible to do. And largely because, well, there's a lot of contextual information here that is not present in just the preceding context in that file. This particular file that we're looking here, affinitypropagation.java, which I think is some code that Danny Tarlow coded up when he was at U of T doing affinity propagation things, which was kind of fun to revisit as a test set for our experiment. So in this particular situation of this file, well, it's actually present in a larger directory of other files, some of which include the class definitions of classes that are being used in the target file. And so in particular, in this case, there's this class here that instantiated, and the definition of that class is actually in another file, in another directory as part of this code repository. And in particular, if you went in that file, you would see that it has the definition of this class here, this method here, initialized to assignment, and that happens to be the answer here. So, if the large language model could actually have access to this, that's maybe its only way really of guessing that this is what it should write here. Otherwise, there's no way of thinking how did this person in this particular file actually define different methods for this object, for this class here. And so now the problem is the large language model, it's been trying to only look at the previous context. This is actually less true now, and partly that was kind of the innovation in this work, is to actually go beyond this. But at the time, that was certainly the case. And so we were thinking, okay, well, how do we provide this additional contextual information to a large language model and still have it use it successfully, despite the fact that it's never been trained this way? So, and this is the knowledge mobilization part. We're kind of trying to test here, to what extent does a large language model like that has learned to generalize beyond the sort of its training experience, where the only thing it would see is only code that came that were from the same file and that came just before. it wouldn't have seen code that comes from an entirely different file and even like a method definition from another class. But if we provide that as input, can it still succeed? So in a way, like it's now I think we sort of know that this can actually work. And part of the inspiration of doing this is that we knew that training large language models is in a way kind of leads to a form of meta-learning. It leads to an ability of learning from examples and from different contexts. And so the idea here was to see, well, do large language models of code actually have this ability where we would be providing this repository level context in it by just generating an augmented prompt. And in this case, what we would want to do is we would take all of this here, so this would be the preceding context we'd feed as a prompt to our large language model. But then further away from this part, we'll also add some additional code that comes from other parts of the repository. Okay, so that's the question we're exploring here. And one of the challenges here is to decide, well, where do we take this code? There are many files in a repository. Some of them are really large. How do we actually pick where to extract this additional code that will paste in here in the prompt that we'll provide? So the way we started exploring this question is we kind of listed the various types of context that we think, contextual information, that we think might be useful for this kind of use case. So we're inserting a little bit of our sort of own expertise as programmers to kind of decide how do we design better inputs, better prompts for a large language model for code completion. And so we came up with this list, or I should say Disha came up with this list of different locations for context that we could fetch. So it could be from the current file, but later in the file as opposed to previously. Of course, making sure we don't actually provide the next line because that would be cheating. It could be a parent class, an import file, a sibling file in the repository. So these are different locations of other code. And then it could be different types of context. So from some given file somewhere else in the repository, I could want to see all the identifiers. I could want to see all of the field declarations or the string literals. So different options here that I could decide different information from these different locations I might want to extract. And so our first approach was to just say, well, let's just list all possible combinations. There are about 60 of them. Let's essentially try them all out. And let's, from that, try to get information to actually predict which ones in different contexts are the right things to use. Okay, so I'll sort of explain how we got to our approach by going through the different results of the paper. So the first one, the baseline that we're trying to beat really is, at the time, was Codex. So a large language model that is really good at doing line completion. And what you're seeing here is its performance. We measured the performance by taking a number of repository that was on Google Code. And so that wasn't on GitHub because we suspected Codex had been trained on GitHub files. And we also we only kept from Google Code the projects that didn't have an equivalent in GitHub. So hopefully by doing this, we're sort of avoiding testing on the training set. Now the success rate, so in terms of completing all of the line that remains at different locations was pretty high. Codex is pretty good at 58.73%. And we also have sort of an averaging that's sort of control for the size of different repository that's looking at the same success rate. And then we'll start looking at how much are we improving compared to this baseline. So the first thing we could do, which is effectively cheating, so that's not really a baseline, but it gives us a sense of the opportunity of doing this, is what we call the oracle. So what we did is that for all of these examples, we would try a prompt with every possible context, location, and type. So as I said, there are about 63 of them, and so we'll try all of them, and we'll just pick any one that works for this example. So really, we're cheating. We're looking at the actual completion, and we're just taking the best possible prompt, the best possible location and type for every individual example. By the way, like when you're doing research, if you have an ability to come up with an oracle that sort of gives you like in the best of worlds, how well could this do? This is kind of useful. This is the first experiment we did just to get a sense of is this possible at all? Is there an opportunity here? Because maybe the results would not have been all that much better from the baseline, and then we'd probably have given up on this idea and moved on. So just generally speaking, I think when you're doing research, that's not a bad thing to do. But now, having done this experiment with the oracle, we essentially also have labels. So for our training set, we can look at what are the contexts, location, and types that actually lead to a success. And then we can train a separate neural net that will take information about just the preceding code and just predict for the different location and types, is it going to be successful if I add it or not? And I can sort of train it on my training set of these examples. I can treat that now as labels. And so what we did then is actually do exactly this with two different neural net architectures for the model that predicts which prompt, location, and context to use. We also looked at another baseline, which is just always use the same location type and the same location, the same type, and just use the one that overall on average is most frequently successful. That was usually looking at the context at the lines after the current line. So this is, if we don't do better than this, there's no point of having a neural net predicting the location and type. That works well. And actually, it turns out that we're getting a significant boost over that fixed rule, and we're overall just doing better than the basic codex. And again, that's despite providing inputs to that large language model that look nothing like it's seen in its training experience. So it had to sort of figure out a way to reason about, this additional contextual information. All right, so these are the three papers, which hopefully gives a sense for everyone here as to what kind of work you can do in that second sort of phase of this framework that I call neural knowledge mobilization. I think there's a lot to do here. I think a lot of this research, as I said, is actually accessible, and it's also important. Some of these ideas explored here, they also end up having a lot of impact. So I encourage people to consider that as well. And I'll just conclude with sort of circling back to a little bit of my journey, what I feel that I've learned with time, what I think might be useful lessons for people here to consider, and the sort of way that I like to think us as an AI community, how we should approach doing all of this work together and making progress in AI. So the first thing that I've grown to prefer, and I think is a better approach in terms of thinking about the research problem that we look at, is to go about it as an engineering first endeavor. And what I mean by that is that engineering is essentially just taking scientific facts and knowledge and deploying it to solve problems that are difficult and all solved, and that would lead to progress on certain societal goals that we want to achieve. And that's as opposed to just exploring questions just for the sake of these questions being scientifically interesting. I think this is great when this happens, and obviously you want both. But I think when you do this, you sort of lose sight of why is it that we're doing all of this work? We're not doing just the sake of curiosity. I mean, that's an internal motivation. But really, the reason why this is all valuable is that we're solving concrete goals that are useful for society. In many ways, the few-shot learning research agenda that I developed, and some of the ideas were directly inspired by actually seeing people in practice not able to solve certain problems because they didn't have the skill to train machine learning models, and they didn't have a lot of data. But this still led to really interesting scientific questions to explore, but at least it was sort of grounded in problems and informed my research in a way that I think just made my research better. And so I think that that's a better approach than just, building AGI for building AGI, for instance. I also think that it's better to approach it as a community endeavor as opposed to an individual endeavor. So the individual endeavor sort of mindset would be, okay, well, many individuals, they're competing to try to make as much progress as possible. And yeah, competition is a good framework sometimes to achieve great things. But I would advocate for friendly competition, or something where we're using competition as a mechanism, but because we're trying to lift each other up and just try to do better work. And there's a lot of reason why it makes sense also to kind of be coordinating as opposed to be strictly competing. The amount of compute resources available just generally on this planet is limited. The amount of human resources are so limited. There are a lot of open questions, and there are a lot of these problems we can't make progress too fast. We want to solve these problems as soon as we can. This is why I like the idea of thinking about working on knowledge mobilization. What you're doing there, in some ways, is recycling deep learning resources. You're recycling compute that was used for something else to do some other thing cheaper, with less resources, with less data. And in terms of using our own time and sort of spreading our expertise to solve as many problems as possible, this has been, to me, a big motivation for starting the journal TMLR, sort of trying to move away from kind of a conference-based assessment of the quality of work, which oftentimes is influenced by, is it significant, is it exciting, to let's just do science, let's just make claims, back them with evidence, and that should be what drives whether or not we accept work and sort of give it a stamp of approval, which is very much what sort of is driving TMLR. And also kind of encouraging a sort of healthier reviewing ecosystem, because that's another part of our contribution in this community, is to evaluate other people's work, giving it feedback, again, trying to lift it up and make it better. And so I think, to me, this leads to really embracing this collective nature of doing research. This is sort of why I try to draw connections of some of my really early work, which in many ways was very toyish. And I mentioned a lot of our experiments were on MNIST. And for many people, this was kind of stupid. This was not really interesting. But actually, we explored ideas that are now really useful. And even if some people feel like even then we weren't really demonstrating things, I still believe that, and that is a huge motivator. And I think I encourage people to embrace that mindset, to sort of focus on, what is your own contribution, even if some people don't really see it. The reality is that we're so connected that it does exist. Sometimes some of our ideas have not first-order effects, but second-order, third-order, fourth-order. So it's important to believe in this, because that really, at least for me, really keeps me motivated. Just generally seeking opportunities to create these ways of interacting. Certainly deep learning in Indaba is an amazing example of that. And again, we can't have too many of these opportunities. And generally speaking, if you think of this as we're all moving forward together in solving AI problems, really the way of then behaving is not to work on the thing that's most popular, it's to work on the thing that no one else is working on. And in many times in my career, that's what I tried to do. So the meta-learning work for free-shot learning that I mentioned, that was sort of me trying to move away from other things that were more popular at the time and just focusing on a problem that I felt no one was really exploring sufficiently at that time. And the work that I talked about on doing code completion, Disha, when she started her PhD, she started working directly in machine learning applied to software engineering and development. At the time, that was a very small community. It was not big. It was not all that popular. And in fact, we had conversations together where she said she felt a little bit alone in this field, and sometimes this was kind of tough. Now it's a huge thing. It's a big, important problem. Lots of people are working on it. And it doesn't always work out this way, but sometimes it does. And when it does, it feels great. And it's really useful for the field again. So really, I encourage people to have this mindset, looking at the unexplored problem and try to be the thought leader in that. And that tends to be really rewarding for yourself and also for the field in general. And if you ever have this temptation of, right now, it seems, as I mentioned, there's a lot of attention on training these large models to do this neural knowledge acquisition part. But just for me anyways, the reason why I feel comfortable moving away from that part of the framework and focusing on other things is that the reality is that today's large scale is tomorrow's small scale. So the scale of the work that you do, it matters a little bit. It's not true that it doesn't matter at all. But the reality is that the context in which we do our research right now, there's a risk that it won't matter so much, in a couple of years or 3 years. So whatever scale that you are capable of working in, if it allows you to explore, good ideas and really creative ideas, things are completely different. When we were working on MNIST with neural nets were not popular at the time. We were a very small number of people doing this. Some people thought it was stupid to do that, but it really paid off because we were really creative in the ideas that we explored, and they turned out to pan out. So, and I'm sure there are still some of these creative ideas that are needed now that can be explored on the scale that's accessible. And finally, as another advice in terms of how might you find this unexplored area, more recently, the advice I tend to give when I have more junior people asking me what they should work on I say now is a pretty good moment to actually look at the intersection of AI and some related field or different field where maybe AI is not as prevalent. We have a pretty good toolkit right now to solve a lot of downstream problems. I have been particularly interested in anything related to sustainability and protecting the environment. So in the past year or so, I've found some collaborators to work on things related, for instance, to biodiversity, using remote sensing to produce some insights as to the state of some local environment when it comes to its biodiversity. This is some of the first work that I've had the chance to be involved in, and that's getting a little bit of a spotlight with Melisande, you're seeing here, David Rolnick, and Benjamin. It's on archive if you want to check it out. It got a recognition as a Best Paper Award at a workshop I think that was at iClear. It's been really fascinating for me to work in this area. I know nothing about, well, I know more now. I wouldn't say nothing, but I'm certainly not an expert. My expertise is not that, but I'm learning a whole lot. And, I like to think that maybe this is a little bit like my experience when I started working on AI for code, and that then it was sort of a niche area, and later maybe it'll be actually a really big area. And I was just at ICML, and to my surprise, I found at least 3 papers that were, core machine learning papers, but their experiments were grounded in these kinds of problems, which I feel is something that, I perhaps would not have seen, 2 years or 3 years or 4 years ago, or certainly not as much. And finally, I'll just say a few words about Mila. I've talked about some of the work here that is actually in collaboration with Mila collaborators. Mila is here as well, as you know, and there's a social tonight as well that people could register to. But I do, I feel it's only fair for me to recognize their contribution by giving them a little bit of a spotlight. So Mila, and that's something that's really appealing to me. That's one of the reasons why I contribute and I'm a member of Mila, is that it has this sort of AI for social good part of its mission, touching a lot of different areas. The one that's really interesting to me has been the environment. It's a really large community, so it's 6 universities in Quebec, many universities in Montreal. They're counting 1,000+ students really that are affiliated in some way or another with Mila. It's bilingual. I hear there's a lot of French-speaking people here, so it's a really nurturing environment and really rich in terms of experiences and people and problems people are tackling. There's both really amazing academic research and some research that's in collaboration, that's more applied and sometimes with the industrial partner. On the academic side, there are a lot of really great professors in different areas with pretty tremendous research output. Again, in terms of being creative, and I think of the kind of fundamental research as being best nurtured by putting together in the same place a lot of people working on different things and exploring their intersections. Because these intersections, if they're areas that are different, they're likely to be new and perhaps transformative. And so really have this kind of environment at Mila, I find. These are examples of some collaborations. The one in the middle is with Hydro-Québec, which is the government supplier of hydroelectricity. And they have projects related to sort of sustainable energy production that are really cool. And yeah, there's a lot of different partners. Google DeepMind is one of them. There's a lot of many, so it's a really rich environment to learn in this area of AI research. And yeah, this is just a reminder for people registered of the social at 8:30. Looking forward to chatting with people. And with that, I'll stop here. Thank you. Happy to take questions now, I guess, or should we wrap up? I realize we're 10:30. Yeah? Any question? I see a hand here. Okay, there you go. Mic is over there.
Thank you so much for your talk. It was very interesting. So just a question on the universal representation. I was wondering in the context of knowledge distillation, it seems like kind of a similar topic to some extent. Would you say the same approach would kind of easily translate to that, acquiring knowledge from many different backbones to train a tiny little model that just kind of compresses knowledge from many. And also in the context of curriculum learning, I wonder if like multiple backbones can also be used to perhaps devise like a curriculum again to train something smaller and simpler, but in a better way.
Yeah, I
It's
think
just
this is
your
all.
opinion.
Yeah, this is very relevant. I think you will also find right now definitely some research based on distillation that is doing this idea of sort of distilling knowledge from. I feel I've seen this. I'm blanking unfortunately on the exact work, but I think if you look for some of these keywords, you'll definitely find some research, and I think it's a very useful concept, knowledge distillation. I think we can do a lot with it, and the idea of potentially compressing various sources of information sounds like one that's sort of perfect for that concept for sure. Yeah, I agree. Any other question? Maybe everyone wants coffee. Is there a hand trying to see? Oh, there's a hand, okay.
Sorry, I made you walk so far. Hi, Maria, my name. Thanks so much for the talk. I've got a question about like the very beginning when you said your interest is to close the gaps to humans, and then the approach you take is considering basically, backbones, pre-trained models. You just get very general models, and how do you like kind of fine-tune them? But obviously, there's another side of the coin, which would be inductive bias and baking it somehow into models. And I just want to throw this at you and see what's coming back in the sense of, is this actually dead because it's too specific? Will this only be applicable to like machine learning, for example, in science, where you actually have models of the world? Or is this the big unexplored idea that we're missing at the moment? Mm-hmm. What's your stance there?
Yeah, that's a great question. I think this is an unknown, which is, and in many ways really defines our field, is how much inductive bias or how much sort of prior knowledge we should put in our model to enable a lot of things we want to do. Deep learning was kind of a lesson of like, well, not a whole lot. If you have a lot of data, maybe you can still capturing in a way that seems, different. They're neural in a very loose way, right? These models. But I think in other areas, I think that's a good point. Like it might be that there's certainly a lot of scientific knowledge in other areas, associated with, say, natural sciences and whatnot, that might be captured. It might be representable in something different than a backbone. I could imagine doing things where however, I have a toolkit that when it's in the shape of the neural net, we're actually decently good right now at mobilizing that knowledge in that form towards other tasks that are represented by examples. So maybe this kind of suggests, distilling some of this knowledge, if it's represented in a non-neural form, to first distill it as a neural net, and then treat that as one backbone, and then sort of leverage all of the sort of neural-based tooling that we have for solving downstream tasks. But I think this is a very relevant question and kind of open question as to, should we put more inductive bias in these models or not? I have found a lot of the work that comes from, Yoshua Benjo, Anirudh Goyal, and Mike Moser has been involved as well. Just trying to take inspiration from, I think it's called workspace theory in neuroscience, and sort of thinking about, sort of what is our high-level representation of how we reason to try to put that into our neural models. I have found that to be kind of an interesting trend. I don't feel it's quite there yet in terms of demonstrating that this should replace the transformer or anything like that, or other sort of successful architectures. But to me, it's great that people are doing that. I think we do need people to explore that sort of branch and philosophy of research. Thank you.
Okay. Hello, Hugo.
Where are you? I have a huge spotlight in my face.
Just north of you, straight ahead.
Okay. I'm probably not looking at you right now.
I would stand maybe. Oops,
okay, all right.
Yes, that happened. So just quickly, 2 questions on the same project, the meta-learning project. So first is, I was just wondering, so you've built this framework for learning to learn, where the model ultimately selects the best backbone for the task at hand. And I was just wondering how you see that scaling, though, because the problem here is few-shot learning. And so if you always need data in the domain to train each new task, then it's no more few-shot, is it? Or is there a solution there that I didn't pick up?
Yeah. No, go ahead.
Yeah, and just the second part is if you have any philosophical thoughts around how this extends into, say, multiple modalities.
Yeah. No, great question. So, oh, my battery's going to die. I guess that's fine. I mean, part of the scaling difficulty with this work is potentially if we actually have, you know, like hundreds or thousands of backbones, retrieving all of them, like in the way that I represented it, that would be challenging computationally for sure. I think we would need to sort of now start digging a little bit more into the details of how can we sort of not rely so much on a dense, soft attention. How could we represent tasks and backbones in a way that doesn't require to sort of visit every single backbone whenever we're solving a downstream task. I think those are future questions worth exploring. You know, there is some work in general for supporting sort of very efficient searching or querying mechanism that potentially we could leverage. And in some ways, I guess there is an assumption that right now there is a lot of data of some kind, and there are a lot of models that are being trained on all of this data. I guess the assumption is that there will never be enough to sort of directly, explicitly cover some downstream tasks, but perhaps by combining these, we can get close enough to sort of boost our ability to solve these downstream tasks. And I think that general sort of philosophy applies. And then in terms of multimodality, I think that's a really good question. I could imagine having, you know, there's situations where we might have backbones trained on different modalities, so doing meta learning to try to learn how to combine these in the best way possible sounds very interesting. I can't think of any work that's done that actually, so that sounds really interesting. And it's also interesting because if we have models that are sort of, you know, modality specific, and then depending on the downstream tasks, certain modalities applies, others don't, there's an opportunity here for meta learning to be particularly useful, because that would sort of suggest that the way of adapting, you know, and combining backbones might be, like that space of kind of operations might be rich enough that it's better to learn it than to try to define it in hand. Yeah, I think this is a really interesting direction to explore. It's a good idea. Thanks. All right.
Sorry, sound. Hi, Hugo.
Hi.
Okay.
I am not looking at the right place, I'm pretty sure. But I hear you.
Okay. Thanks for the talk.
Okay.
On the section where you spoke about like applying attention to the different backbones, if you use multi-headed attention and select multiple backbones, do you concatenate the different representations, or do you average the different representations? And then like a follow-up question to that is, I assume there's been work on like taking multiple backbones and applying some representation network and taking in all the input from the backbones and like outputting a simpler representation. I'm just trying to understand why, like, is that a bad idea? Does that not work well when you have multiple backbones?
Yeah, so a good question. So for the first one, you do concatenate the retrieve representation. So in my case, I had 2 attention head. So I ended up concatenating 2 retrieve representation. And so essentially the number of heads is kind of like, it controls how large the representations are going to be ultimately, how many concatenations you're going to be doing ultimately. And I mean, I think in many ways, I don't think this is necessarily the final solution. The way we, because in many ways what we're doing here is essentially a model that takes in many representations and then combines them or compresses them into something that's simpler. You could also kind of, you know, describe the method that I showed here as essentially doing that. And so there might be other approaches. We built on top of, we were inspired by some work that was starting with the concatenation and then had this like other way of sort of sparsely selecting the right features. and with really good results. So we were impressed by these results, and we thought, okay, well, maybe there's another approach for doing this kind of, let's take what is really a rich set of features and get a more targeted representation that's more compressed for a downstream task. It happened to do better here. I don't have it's hard to exactly explain the very specific reasons why it's doing better, except for saying that perhaps we're sort of less, we're taking less risks in terms of overfitting due to the really high dimensionality of thinking of it as like concatenating all the representations. And so I would maybe sort of pay attention to that, but there are many ways of effectively controlling the capacity of a model that takes in a large dimensional input. Essentially, this transformer layer is one way of doing it. I'm sure you could imagine others, and maybe some of them would be better. So I think this could be an avenue of further improvement. Yeah.
Yes.
Sure. One more question?
Yeah. So I have a question.
Okay.
It's just a follow-up to what he has mentioned about concatenation. Is it possible to apply cross attention before the concatenation instead of just taking the queries and the values from the same modalities? Like cross attention can be a little bit helpful before concatenating the features. Is that one possible?
Yeah, that's a great question. So we explored something like that. Like in a way, when I was thinking about the trajectory of this work, I was thinking like the one layer version is kind of the first step, but then maybe we can add now more transformer layers, slightly adjusted to allow for forms of cross attentions across the representation, and perhaps sort of implement a version of what you're referring to. We never got anywhere by adding this extra complexity, and I don't quite know why. I mean, maybe it's a property of the framework we were looking at, or the benchmark. I mean, the benchmark had, some. It didn't have a huge diversity of types of tasks that we could do meta learning on. It was just these. Was it like 8 or 10 different sources of data? If we had a richer set of data, maybe we could have sort of improve or increase the capacity of the model and get something even better. My advice would probably be to do that. Just like revisit this idea, maybe revisit the benchmark, make it perhaps more diverse in terms of the types of problems that are being considered and tasks. And there maybe this kind of direction might lead to improvement. So, but it's a good thought. Yeah, I agree. It would be something worth investigating. Thanks.
Well, let's thank Hugo again for the great talk and amazing thoughts to leave us with. Thank you very much. I would just, if this works, leave you with this again. We are about to start the workshops, so make sure to check the schedule so you are sure to go to the workshop that you are interested in. We have a bunch of amazing ones, so I hope you will enjoy. Have a good day, everyone.